Hey, welcome to The Explainer. Today we're going to tackle a term you see absolutely everywhere. From news reports to medical studies, the confidence interval. We're going to break down what it is, how it works, and most importantly, how you can use it to figure out if a study's findings are actually the real deal.
So have you ever seen a political poll of like 1,000 people and wondered, how can they possibly know what an entire country is thinking? Or how a new drug that was only tested on a few hundred people gets approved for millions? It really gets at the heart of statistics, right? How can this tiny little snapshot tell us something meaningful about the whole massive picture?
And that's really the big challenge we're up against. Imagine we want to find out the average age of all graduate students in the country. Well, we can't ask every single one of them. It's just not possible. So we have to take a sample, a smaller, manageable group. But the moment we do that, we've introduced some uncertainty.
Now, if our sample of students has an average age of, say, 33, it's super tempting to just say, okay, the answer is 33, and call it a day. But that's just a single guess, a point estimate, and let's be honest, it's almost definitely not exactly right. What we really need is a tool that gives us a plausible range, a tool that actually works with that uncertainty instead of ignoring it.
And that tool, my friends, is the confidence interval. Think of it as our statistical fishing net. It's what we use to try and catch the true answer that's swimming around in that big lake of uncertainty. It's one of the most powerful and common tools in all of statistics, so let's see how it works.
So what is it really? Well, put simply, a confidence interval is a range of values. Instead of guessing one single number, we calculate a lower number and an upper number. And the whole idea is that we can be pretty darn sure that the real answer for the entire population, like the true average age of all those students, is somewhere between those two numbers.
The best way to get this is the fishing net analogy. Okay, so imagine the true average we're looking for is one single fish in a giant lake. Every time we take a sample and calculate a confidence interval, it's like casting a net. Now, a 95% confidence level doesn't mean there's a 95% chance that the fish is in the one net we just threw. What it means is that our method of casting the net is really good. If we were to do this 100 times, we'd expect our net to catch the fish 95 of those times. It's about how reliable our process is.
Now, in some kind of perfect, magical world where we already knew stuff about the entire population, like its true standard deviation, we'd use this really clean, simple formula.
But come on, let's be real. If we already had the data for the whole population, we wouldn't need to be estimating anything in the first place, right? The whole reason we're doing this is because we only have data from our small sample.
So, this is the formula we actually use in the real world. It might look a little intimidating, but it's not, I promise. Each piece has a job to do, and together they build our statistical net. And you'll notice it uses different symbols because it's built using only the information we can get from our sample.
First up, we've got x hat. All this is the average or the mean from our sample. That's it. It's our best single guess, and it's going to be the exact center point of our range. It's our anchor.
Okay, this next bit is called the standard error, and it's actually pretty brilliant. It combines S, which is just a measure of how spread out our data is, with N, our sample size. And think about it. This makes total sense. If you have a really big sample, or if everyone's answers are clustered really close together, this whole part gets smaller. And a smaller error means you have a more precise guess.
And finally, there's Z star. This is our multiplier. This little number determines how wide we cast our net. If we want to be 95% confident, which is the most common level, we use a Z-star of about 2. This means our range is going to stretch out about 2 standard errors on either side of our sample mean. If you wanted to be, say, 99% confident, you'd need a bigger multiplier and an even wider net.
Okay, that's enough theory. Let's get our hands dirty and actually put this formula to work. We're going to walk through a real example step by step.
All right. Let's go back to our graduate students. We survey 30 of them. We find their average age is 33, and the standard deviation is 4.3 years. So, step 1, we start with our best guess, 33. That's the center of our interval. Step 2, we calculate that standard error to figure out how precise our guess is. Then, step 3, we create the margin of error by multiplying that standard error by our Z-star, which is about 2. And for the final step, we just take that margin of error and add it to 33 and subtract it from 33. That gives us our range.
And boom, there it is. Our confidence interval is from about 31.4 to 34.6 years. So what does this mean? It means we are 95% confident that the true average age of every single graduate student at that university is somewhere in that range. Pretty cool, right? We took a tiny sample and made a really reliable estimate about the whole group.
Now hang on, this is a super important point, and it's where a lot of people get tripped up. This interval, from 31.4 to 34.6, is our guess for the average age. It absolutely does not mean that 95% of all students are between those ages. I mean, of course there are going to be students who are 25 or 45 or 50. This interval is all about pinning down the average, not the range of every single person.
So finding the range for one group is pretty useful, but where confidence intervals really shine is when we start comparing two different groups. This is probably where you'll see them most often out in the wild. So let's say a study is comparing two weight loss methods. The diet group lost an average of 7.2 kilograms. The exercise group lost an average of 4.0 kilograms. I mean, okay, 7.2 is obviously more than 4.0. But here's the multi-million-dollar question. Is that difference actually real and meaningful, or could it just be a fluke based on the specific people who ended up in our study?
This is the question that keeps researchers up at night. Is the difference we see in our samples big enough, reliable enough, to say that there's a real difference between these two approaches for the population as a whole? Well, a confidence interval for the difference between the groups is exactly how we find out.
The good news is, you're not always going to have to calculate this stuff yourself. Most of the time, you'll just see it presented in a table, in a study, or a news article. So let's figure out how to read one.
Okay, check out this table. It's comparing mothers who smoked more than 10 cigarettes a day during pregnancy with mothers who didn't smoke at all. Now, let's focus on the line for maternal education. You can see the average years of education are a little different, but the column you really want to look at is the one on the far right, the one that shows the difference, and it's 95% confidence interval.
So right there, that's the key. The confidence interval for the difference in years of education between these two groups of mothers is from 0.15 up to 1.19. Now, here comes the most important part of this whole explainer. Look closely at that range. Is the number 0 in there? Nope, it's not. The whole range is above 0. So let's wrap this all up. When you're looking at a study that compares two groups, whether it's a new drug versus a placebo or one marketing campaign versus another, find the confidence interval for the difference between them. And here's the golden rule. If that range, that statistical net, does not contain the number 0, that is a huge flashing sign. It tells you that the difference between the two groups is probably real. It's statistically significant. And that right there is the secret to reading these studies like a pro. So, the next time you see a poll in the news that mentions a margin of error, which is just part of a confidence interval, or you read a headline about some new scientific breakthrough, you've got the tools to dig a little deeper. You can look past the splashy claims, find that confidence interval, and decide for yourself how much you should really believe the results. So, what are you going to look for now?